Mr. Chairman and honorable audience, my name is Wang Song. I'm from the University of Hong Kong. Today, I want to present my paper, Multi-Modal Sensor and Data Processing for Comprehensive Skin Evaluation. Skin is the largest organ of our human body. It plays an important role in protecting our body, such as adjusting our body temperature, preventing dehydration and harmful bacteria. Its appearance also greatly contributes to others' perception of our appearance. Brighter skin color and smoother skin surface will give others the impression of being healthy and attractive. So everyone cares about skin state. But what's the most important is that there are lots of terrible skin disease, especially the malignant melanoma, with very high mortality rate. Everyone wants early detection and treatment. Currently, there are lots of skin testing equipment for scientific usage or cosmetic purpose. The technologies they use include optical image analysis, biological impedance analysis, and various specialized technologies realized by multi-probes. Among them, the optical image analysis can be easily integrated with cell phone, but it cannot measure mechanical skin properties. Multi-probe equipment is too complex without portability. So here we find that currently there lacks a skin testing device able to simultaneously measure both optical and mechanical skin properties with a simple structure. This work seeks to fill this research gap. To this end, we need to find a feasible sensing principle and design the sensor structure, as well as develop its corresponding data analysis algorithms. This is the skin sensor prototype we have designed based on the principle of frustrated total internal reflection. It consists of a smartphone and a probe fabricated by 3D printing. They can communicate through wire connection. The probe includes a plano-convex glass plate on its top and a high-resolution camera on its bottom. Around the glass plate, there is a LED light source injecting light into the glass plate from its edge. So if nothing touches the glass plate, no light will leak out of the glass plate because of total internal reflection. But when the probe is pressed on skin surface, haptic or optical images of skin surface can be formed according to different contact forces. The shell of the probe consists of two concentric cylinders connected by a spring. Contacting with the skin surface will induce compression of the spring. The compression amount can be revealed by the FOV size of the camera. This will further reveal the contact force. The skin sensor can realize multimodal sensing to simultaneously measure optical and mechanical skin properties simply in one single operating cycle. First, when the contact force between the glass plate and the skin surface is gentle, a haptic image with distributed bright and dark areas can be captured. The 3D microstructure of the skin surface can be recovered from this haptic image so that skin roughness can be calculated. Then when the glass plate contacts tightly with the skin surface, an optical image of skin surface can be captured. Various optical skin properties can be analyzed, like skin pore size. Then, by slowly releasing the contact force before the separation between the glass plate and the skin surface, because of the convex shape of the glass plate, a contact image can be captured. By approximating the skin surface as a Winkler foundation, skin deformation amount can be calculated from the bright spot size. The bright spot size inside the FOV area. Finally, according to the difference between the FOV size of the contact image and the reference image captured after the separation between the glass plate and the skin surface, the contact force can be figured out. Combining the contact force value and the skin deformation amount, the skin elasticity can be calculated. The optical skin images can be used to analyze various optical skin properties. Here, the average skin pore size is taken as an example. The skin pores are recognized through an adaptive threshold method. A small sliding window is used to determine every pixel whether it belongs to a skin pore or not. Specifically, a threshold value is calculated by averaging the pixels inside the window. The center pixel of the window is determined as the skin pore if its value is below the threshold. By this way, a binary image indicating the skin pores can be generated. Then, morphological operations like dilation and erosion are taken to filter out the noise. So a clear markup of skin pores can be generated. So the average skin pore size can be calculated. The haptic skin images are captured under gentle contact force. According to the principle of frustrated total internal reflection, the relationship between the pixel value and the contact force is linear under gentle contact. The skin deformation under gentle contact force is also linear. So the pixel value itself is an indicator of the 3D skin surface structure. Here, a polynomial plan is used to fit the haptic image, and it is regarded as the macroscopic shape of skin surface. Then, this macroscopic shape is subtracted to generate the microscopic 3D surface structure. The variance of the residue is used to evaluate the skin roughness. It should be noted that the calculated roughness is not the physical skin roughness, but can be used to evaluate the relative change of skin roughness between different measurements. Experiments have been conducted with the testee to verify the skin pore size measurement and the roughness measurement process. The mouse corner of the testee is chosen as the target area. Measurement was first conducted in normal skin state and after cleaned by normal water for reference purpose as shown by the red and blue dashed lines. Then the testee applied some toner to his face and measurements were taken every 10 minutes as shown by the black line. The results show that clean and toner barely have any impact on skin pore size, but they can greatly reduce skin roughness, especially for the toner. But the effect of the toner can only last slightly more than 1 hour. This experimental result conforms to the utility of the used toner and visual perception. So it proves the effectiveness of the skin sensor in measurement of optical skin properties and skin roughness. Experiment has been conducted to capture different FOV size under different contact forces, so that the relationship between contact force and FOV size can be calibrated. Therefore, for a contact image, the contact force can be determined according to its FOV size. The contact area can be segmented by a Canning operator so that the deformation of the skin surface can be estimated. Finally, the skin elasticity can be calculated. For validation, four measurements are taken on the testee's face, including his temple, eye bag, cheek, and mouth corner. The elasticity values are all on the same order of magnitude. The differences at these areas are also consistent with hand feeling. So this experiment result proves the effectiveness of the skin sensor in measurement of skin elasticity. In conclusion, I want to summarize the potential contributions of the skin sensor. The skin sensor extends the principle of frustrated total internal reflection to cosmetic area. and realize the simultaneous measurement of both optical and mechanical skin properties with a simple structure. It is very suitable for daily skin monitoring and has great potential to be used in dermatology. That's all for today's presentation. Thank you for your attention.